Welcome back. All right. We're talking about the actual pump, not a theoretical pump.
Yeah, see, it's not going to work.
We said if the restrictions opened up, pressure
Stays
stays the same. I said stays. Stays the same. If restriction is closed, pressure stays the same. What if it's closed all the way off? Pressure stays the same. Pump is sped up, pressure
Stays the same.
and it pumps slowed down, pressure.
Stays the same.
Okay, so in a few weeks from now, you're actually going to build one of these pumps. You're going to take a pump apart, do the oil, put it back together. You're going to put it on a stand. You're going to run it, and I can measure flow rate and pressure output. And so I'm going to ask you all these questions. And I hope that you get it right. But this is only to a point. Now, when I say it stays the same, it may not stay exactly the same. It may change by a slight bit. If I have it set for 20 psi and it's running and I close the orifice all the way off, yeah, it may go to 21 psi, but that is roughly the same. And I'm going to tell you, and it even says that when you do the oral on this, if you say it goes up and it goes up by like 1 psi, you're wrong. That's staying the same. So when you say goes up, that means it goes up. Yes.
Like more than 3.
Like more than that much.
I'm just trying to figure out what that cutoff is. Because if we're talking 2
It's to that
psi,
point.
it
You're trying to
goes
find
up
that
1
point.
psi. That's double.
Then be specific.
Okay.
Hey, it's going to go up like a psi.
Yeah.
But if you say it goes up, I'm expecting to go from 20 to 40.
Fair enough.
Or 60 or 80.
That's the point.
Yeah. But if you know what you're talking about, you know it goes up by a psi, you'd say, if I say is it going to go up, down, or stay the same? You say, well, it's going to go up like 1 psi, but right?
Stay the same.
Then we don't have a problem. You say it goes up and it stays, okay. So, when you're running this pump, and we got it on a stand so we can actually measure flow and pressure, which you will. And if we're running it at, let's say, we'll start at the top, restrictions opened. Okay, we're running it at a certain PSI. Okay? And you have an orifice on the output of the pump. Mind you, that's not inside the pump, it's outside the pump. And so we're measuring flow from the outlet of the pump out here, and then there's restriction.
Mm-hmm.
Right. Pressure. We write it. So we have pump. There. It's on the scale. A valve. Let's see. Flow. So how to measure flow. That just goes overboard. And we'll put the pressure here. I think that's pretty much how it is. All right, so if it looks like that, follow? Mm-hmm. Okay, so if I have it running and I have a restriction with a certain amount of flow, we'll just give it like 20 gallons per hour or something like that. We're just making up numbers. And we have, let's say, 40 psi in scenario number 1. Well, we're running it. And then scenario number 1, I open the restrictions. I open up the restriction right here, open it up a little bit. What happens to the pressure?
Stays the same.
Stays the same because it's got a pressure regulator on top. What happens to the flow?
Flow increases.
Why does the flow increase?
Because you open the restriction.
Open the restriction?
You open the restriction, so
But the
there's
pump
no
didn't
more.
go faster or slower.
Doesn't have to.
It doesn't.
The restriction opened up.
Allow more volume through.
Some more volume came through.
It pumps the same amount of volume, just not
Yeah.
the same.
Now think about it this way. If the pump is pumping a certain amount of volume, let's say it's pumping internally it's pumping 100 gallons per hour. Right now in my drawing, how much is leaving the pump?
20.
How much is recirculating inside?
80.
There we go.
Yeah.
Okay? So I open up the orifice a little bit more. Instead of 20, I've got 30 gallons per hour.
Now 70 is recirculating.
70 recircs. 30 goes out, and what's my pressure do? Stays the same. Okay. 2. We'll go 2. Now I close off this restriction.
Flow goes down.
Okay. What's my pressure do?
Same.
What was it again?
40.
Pressure stays the same. What's flow do? Goes down. I didn't close it all the way. If I close it most of the way, it goes to what, 10?
Yeah.
Then what's recircs inside? 90. Okay. What if I close it off all the way? Pressure goes to,
It's the same.
Stays same.
stays the same. How much recirculates?
100.
And how much comes out? Okay. Now I'm going to speed the pump way up. Okay, I double the speed. All right, sounds fair. 200 gallons per hour. What happened to the pressure?
Stays the same.
Stays the same. What happened to the flow?
Stays the same.
Well, if I haven't changed it, and a minute ago it was 10, and in my old scenario, what is it now?
20.
The orifice is the same?
Yeah,
20.
stays the same. Why does it stay the same?
Because
Because it's the same pressure.
Bye.
Did I lose you?
It's because of the restriction.
Let's do it. Yeah. Maybe if I did it this way.
It's kind of like the main metering chip in the car. No matter, like it's restricting this maximum amount that flows through regardless the pressure.
Okay. It's more like a magneto. No, I'm just kidding. All right, let's try that one more time.
Wait, so in this case, pressure, so because pressure stays the same, the only thing that you're being focused on is whether or not it's open or closed? And the volume of
I didn't hear that.
The volume's dependent on the orifice.
Let her speak for herself. You don't need to mansplain. What is it? I was just repeating what you said.
it? So,
Did you mansplain to me? What she said. That's worse.
mansplain to a man.
so in this case, like where pressure stays the same, but so what we're paying attention to is, oh my god, never mind.
Okay.
I'll just ask it. So,
I'm going to do this one more time.
That's just explain.
So what if the pump was at 100 gallons per hour,
yeah.
okay, and the pressure here, we'll say is 40, and the flow is, and we got to do something here. So this will be how far it's open. Open. That was it. Okay, quarter. It's quarter way open.
Okay.
And our flow is 10 gallons per hour. Okay? So
So the returns.
now I'm going to speed the pump up. Okay? Speed up. Speed up. So now internally, and this is, I just made all this up. I've never done it like this before. You don't know what's happening in the pump, but maybe it helps you to see it. So now the pump is capable of 200 gallons per hour because it's spinning a lot faster. Okay? And I didn't change the orifice. So that means the pressure is going to be,
The same.
why does the pressure stay the same?
Because
Because it's got a regulator on top,
regulating
regulating it. Okay? And because it's still 40 gallons per hour, 40 psi across a quarter opening, the flow is
still 10.
the same. Well, what if I speed up again
Still stays the same?
to 20,000
You might break it, man.
gallons per hour? Now what happens?
You'll need a stronger
Zero pressure.
140,000, I don't know. And flow?
Well, would that
Yes.
still be a quarter of?
Lots. Okay, I say this jokingly, but not as a joke. There comes a point where this little thing inside, let's go back one, where it's easier to see.
This pressure
regulator can only hold
The pressure regulator, it can only go so far open. And it can only provide so much room for the fuel to flow back around. And at some point, it just overwhelms this and will cause the pressure to go way up. I mean, you know, when is that going to happen? Not under normal operating circumstances, but you need to understand that. It could happen. It could happen. The same thing happens if I slow down. I slow all the way down to 10 gallons per hour. That's what we had over here, 10 gallons per hour, right?
Yeah.
And what's my pressure going to be at? Because our pressure regulator,
40.
maybe only 15.
Yeah.
Why?
Oh, because you're not pushing. You're not.
Because the pump is moving so slow, and this pressure relief on the top, it's closed. I'm doing the best I can. I closed. And 100% of what's being pumped is going through the pump. But yet 100% of what's going through the pump, I mean, you could go to extremes. What if I'm doing it at 1 revolution per minute?
Barely moving.
That would be like that. So the pump is moving at that speed. Well, do you think you're going to get 40 psi out of that?
No.
So the pressure is going to be,
Lower.
I mean, it doesn't matter what kind of pressure regulator you got, unless it's magic. It's just going to be like, well, I'm closed. What do you want from me? Right? Okay, so in that case, if its pump's moving so slow, the pressure relief valve is closed, it's not really helping at all, then you're going to get what you're going to get. So if you only had 15 psi and you still kept that a quarter, you know, who knows? You get, I don't know, 1 gallon per hour or something. I'm making up numbers here. Follow?
Mhm.
So that's what I'm saying is you get to a point where the pump it's just a machine. So if you turn it too slow, you're not going to get enough pressure for the pressure regulator to work. If you turn it too fast, you're going to overwhelm the pressure regulator and pressure is going to go up. And if pressure goes up, it means your flow goes up. And if pressure goes down, your flow goes down, assuming the orifice stayed the same. So let's go back to this. Let's say we had 100 gallons per hour. Boy, what am I doing? GHP? GPH? Gallons per hour, GPH. And we're back to our 40 psi, our regular. And I open this up. And we were at 10. Now what are we going to get?
20.
Sure, 20. Remember, these are made up numbers. It's no correlate. I'm just making up numbers. Right? So if we open up the orifice, why'd the pressure stay the same? It's got a pressure regulator. It came down a little bit inside, probably. And we got more flow because
The orifice.
opened up the orifice. Did I cover all the scenarios?
Mhm.
Bigger orifice, smaller orifice. More speed, less speed. Okay?
Yeah.
All right. In reality, all of these numbers are going to change a little bit. Right? Maybe it'll go to 41 or 42. This may go 10 to 11 or 9. And it's going to fluctuate a little bit when you start changing stuff. But
Just about stays the same.
you got to understand, if
Stays within a range.
if pressure stays the same, if pressure stays the same, flow stays the same, unless orifice is changed. I don't know. Maybe I shouldn't have wrote that, but I did. Questions?
At what point does, if the pump is too slow, like turning too slow, what's the point to where it pumps out naturally what it's, like, it's, in this example 40, like, is there like a threshold where?
Oh, it's just pump design. Who knows? Yeah, where's that point where it starts to go too slow that it won't keep up? And where's the point where it speeds up that it overwhelms it? It's going to be based on the pump. Because the pumps are all different size. Depends on the size of the pump, the size of the relief valve. In all practical purposes, the pump is designed so it doesn't really come into effect. So one of the things we do as mechanics, we work on the continental fuel injection system. We have to set it up. And it's a rotary vane pump. And so one of the things you have to do is you have to set up the pressure at the low end, and you have to set pressures at full throttle. And they're not the same. I mean, it's got pressure relief, it's got orifice, it's got all this stuff, but they change. It's designed to do that. So when you idle it, it's like 5 psi. And then when you go to wide open throttle, it's like 25 psi. So they're designed to change, but they're designed to work within a parameter. That probably didn't help right there when I said that. But for this particular pump, I'm going to go out on a limb and say that it's designed so that it keeps pretty much the same pressure across its operating range for the engine that was designed to be put on. Because you don't really have a lot of variation in these engines. It's going to go as slow as how much?
550.
About 550. Everybody should know that. And as fast as about 2,700. Well, it may be geared on here so that it's turning twice that or more, but it's not a wide range, so it should work. Let's see. Operation. B operation. So that was slide 4. See, aren't you glad I didn't move on? I wrote notes. All that stuff right there.
Going over.
What? Nothing. You're over it? Utilizes an eccentric rotor. What does eccentric mean?
It's good at stand-up comedy.
That was pretty good. I was thinking, you know, where's
Go on, Crow.
it's good at stand-up comedy. I was thinking has a lot of cats and
That's a good one too.
means it's not circular. It's ovalish. Rotor driven inside of a cylinder. That's not even right. Hang on. Inside a cylinder. It's not an eccentric rotor. The rotor is very eccentric. The rotor is the thing that moves. So it's got an eccentric cylinder. Yeah.
Actually, I think they're both circular. It's just the axis of one of them is offset from the axis of the other.
Yeah.
There we go.
The cylinder is offset from the
You're correct.
center of the.
I'm looking at
cylinder.
it. It's a perfect circle with a perfect circle. So it has 2 offset circles. Utilizes 2 offset circles.
Oh shit!
He writes it down.
Oh, so
It's got
close.
scribblies all over it.
You should try it. This is the pen.
I know.
Let's see. Ooh. Ah.
Looks like it's a rotor.
Yeah. Yep.
Maybe not quite right, but there you go. Circle inside of a circle that's offset. It's like my cholesterol. What?
Like cholesterol, like levels, too much cholesterol and walk your vein. And actually,
Oh, you got it all wrong, man.
Oh Lord.
I don't know how we got our cholesterol, but
It's like your blood pressure.
What's wrong with you?
they're just lying. They're lying to you, man. Butter and stuff, and fat, it just lubricates your arteries so that everything flows way better. Slots in rotor allow vanes to slide in and out. The best example of that, I don't, is the continental rotary vane. When you watch those, they're really cool how they move back and forth.
I think we should have.
In the video, I do a video with it, but that's in the continental one. Slide in and out. As vanes rotate. Rotate, the volume in the cylinder increases and decreases. We'll say the space. Increases and decreases. All right. Typically speaking, constant displacement. Fuel pumps are designed to deliver is needed. Because it would not be a smart move to design a constant displacement pump, put it on an engine that only provides barely enough fuel for the engine to run. So why would they want to go excess? Because as the pump wears, you don't want it to go, well, I'm not getting full power anymore. I still want to be able to do that. What happens so if fuel pumps are designed to deliver more fuel or pump more fuel than what is needed? What happens to the excess?
Get the pump to circulate.
Yeah,
On this side of the pump.
Yep.
Well, there's a proper way to put that.
Just back to the inlet.
That's on the-
Yes.
on that side of the
Yep.
pump.
Return back to the inlets.
In this case, it's literally the inlet side.
That's what's up.
As opposed to the fuel tank, which is still the inlet side, but not quite.
Yep.
A pressure relief valve adjusts the amount of fuel, adjusts the amount of fuel being returned and thus, hardly get to use the word thus, controls, we'll say pump pressure. All engine-driven pumps must have a mechanism to allow boost pump, fuel to flow through the pump. Called bypass. Bypass. Or starting. For two reasons. One, starting. And two, failure. What happens if the boost pump fails? Well, the engine-driven pump takes over. But let's just say, what happens if you're trying to start the engine and the boost pump fails? How would you start it?
Crank it. I don't know.
Who are my CFIs? What's the answer to that one?
Spin your propeller. What's that?
3 CFIs in here, right?
You don't start it.
Huh?
You fix it. You don't start it.
Just have the gravity fixed.
Check the.
You don't go flying. That's the answer. If your boost pump fails and you're having trouble starting the engine, you don't go flying because you need 2 pumps. Yes.
Unscrew the cylinder cap.
Spark plug. Take the spark plug out, squirt some fuel in there, get it started.
Pray wasn't for sure.
All right. Some pumps are compensated or balanced. I always call it compensated. Or balanced. Let's see, 1, 2, 3, which is use a diaphragm to assist the spring, and increase pump pressure.
That's your pressure relief spring pump.
Hmm? and assist the, I could do that, pressure relief. Pressure relief spring and increase pump pressure when air pressure is increased. So I think I may have talked about this in the video a little bit. I'm a little unsure of this. Use this one. A little unsure of this. So here we have this compensated pump. And if we just left it open to the atmosphere, and we're down here, sea level, how much pressure is in that vent chamber?
Atmosphere.
Atmospheric. Okay. And does it have an effect on the spring?
If you leave the valve open, I don't think so, no.
I kind of feel like it wouldn't. Then we go way up in altitude. And what happens to the pressure in the vent chamber?
Decreases?
It decreases. So does that mean it's helping the spring less or the same as it was before?
Same as it was on both sides of the spring.
As long as you leave the valve open, it shouldn't have an effect.
That's what I think.
Yeah.
But I've seen stuff where it talks about, well, it compensates for going up into altitude. I don't think in this case it does.
I mean, still, it's less pressure on that back side. You got fuel pressure on one side and atmospheric on the other. If the atmospheric pressure is lower,
It wouldn't have an effect because it's just a spring. If you seal it off, then you've got like a chamber. Then
If you sealed it off, that's something different.
Yeah.
So if we were down low at altitude where it's 30 inches, and right as we're taking off, a little bee sticks in. You got a bee butt hanging out there, right? And so we have 30 psi trapped in here. And we go way up in altitude. That means this has a little more pressure. But does it really have an effect because we have surrounding it metal that it doesn't really know that we went up in altitude? I think if it did, it'd be so minimal.
What did you just say?
Look at that bees out
You heard
there.
bee butt when you woke up, huh? Hang on. So it's a hypothetical. I'm not sure if atmospheric pressure plays any sort of role into this. Because I think it's really designed to be connected to something such as a turbocharger or supercharger, where you're significantly increasing the pressure. So I'm just telling you right now, I don't honestly know. Before I used to teach that, as you go up in altitude, then the pressure in here would also decrease. So this is open atmosphere. This would also decrease, right?
Mhm.
We go up in altitude, it decreases, less pressure on the spring, therefore the pump the pressure would drop automatically.
Well, that's when it's open, right?
Yes, when it's open. And then as you would descend, it'd be more atmosphere would go in there, and it would help push down on the diaphragm. That would increase the pressure. I just don't know if that would really happen.
Well, it would probably depend on how strong the spring
Yeah, spring's got pressure.
So it just does an assistance.
What I do know is this. If you hook it up to a supercharger or turbocharger and that spools up, it is going to put pressure in there. It is going to increase it and increase pressure. That's what it does. That's what it's there for. I just don't know how much atmospheric pressure plays a role. It's
I
just
would think it would have
vented.
to be a large chamber for that amount of PSI difference to make that.
For just atmospheric.
You know,
Yeah, that was my thought. It's just not enough to.
I mean, if a small pump with that small chamber, I don't think it would be enough.
Yeah. But I'll show you. When we hook it up and we're actually running these things, I have a large syringe I'll hook up to it. And some of you will remember this. And I'll put it on there and I'll say, so what's going to happen if I increase the pressure on this? And what happens if I increase the pressure on that?
You're going to get
pushes it on the chamber and pushes the pump through.
Okay, it's going to push down. What happens to pressure?
goes up.
Pressure goes up. Then what happens to flow? Pressure went up. What happens to flow?
No, that goes up as well.
Well, the orifice.
Constant displacement.
I'm thinking
Wait,
about
what
just the
did you
pump,
just
not the
say?
orifice end.
If I put, I will. I'll put a syringe and I will push down on it, which will force air into that chamber, which will force it onto the diaphragm, which does what with the spring? Assist or assist? What happens to pressure? Pressure goes up. If pressure goes up across an orifice, what happens to flow?
Increase. Stays the same.
Proportionally goes up.
Gotta get this right. If I increase the pressure, I'm going to increase
If you
the.
looked at it.
The flow.
Flow.
You see, I didn't write all that. If I increase the pressure, then the flow is going to go up.
I keep thinking about just the pump itself, not necessarily the orifice.
Now I've got the pump running, and I've got it set up to the system right here.
Mhm.
And I take a syringe.
Yeah.
I got to draw a syringe. I got to draw a syringe. There we go. Hey, not too bad. Okay. Got to put an O-ring right there. Okay. There we go. Put an O-ring. All right. I put that on there and I go, I shove it in. What happens to pressure? Pressure goes up. Why did it go up? The assist of the spring and it pushed down on that plate. So the pump pressure went up. So now I've got more pressure in this line right here. More pressure in that line. So what's it going to do? Is it going to stay the same across the orifice? Or is it going to push more fluid to the orifice? It's going to push more fluid to the orifice. It means the flow went up.
So more pressure, more
flow.
Yeah, across a given orifice. So what happens if I take that syringe now and I pull back on it real hard?
Decrease the flow.
Decrease pressure, stays the same.
Decrease the pressure. If I decrease the pressure, what happens to flow?
Decrease the flow.
Flow goes down.
Nope, stay the same. April Fools.
Do you understand?
Oh, it is like an April Fool's, that's right.
You're like,
I feel like we can definitely.
she looks at me like a puppy.
That was the thing that I was a
Not
little
like the
bit
front.
confused on when, cause like when you're talking about this drawing. But this is like outside of the pump, or is this supposed to be what's
This
happening
is the pump.
inside?
Oh, okay.
Okay, that's what,
This is the pump.
yes.
That is. Everything else is outside the pump. So, let's see.
Ta-da!
There.
It lines up perfectly.
It's actually lined up spot on, man.
It does line up.
How'd you do that?
That was a good question. So there we are. That's exactly what's happening. At least I got the outlet going the right way. Okay. All right, so- Okay. And when you hook this up on the green machine that you guys walk by all the time, it's exactly what's going to happen. You've got a pump, and you're going to have these fuel lines, and there's going to be an outlet pressure. There's going to be a valve that you get to spin, and there's going to be a flow meter, just like this.
Cool.
And we'll ask you all these questions.
Okay, so when you're, the example that you're just using of assisting the pressure.
This is where I put a syringe on the vent.
Yes.
Okay, yeah, I'll take that out, and I push on it real hard. Oof. Okay? So I increase the pressure up in this air chamber. Up in this air chamber right here. So when I increase that pressure, it pushes down, it helps the spring. If it helps the spring, it's going to push down this plunger right here. If it pushes down that plunger, it means that more pressure goes out, more volume goes out of the pump, less is recirculated. So if more is coming out, that means the pressure goes up across the, because there's an orifice, so pressure goes up. If pressure goes up, it means the flow also went up. All right.
Cherry flavor.
Should I move on or do it again?
No, we're done.
We're good?
I'm still stuck.
Wow. Okay. I got it. Shut up. Move on. Okay. All right. So now that you have that, I'm going to change everything.
Whoa.
No,
Great.
please don't.
All right. So this is cars used to use pump, which is exactly like this. My boat still has one. Right? It's a diaphragm fuel pump. It is not constant displacement. It's a variable displacement. And the way it works, he's going to explain it, and I'm going to have to stop it a couple times while we do it.
What is that coming in? Sorry.
Oh, a fuel pump.
Well,
Very-
you said something just like
Very
Diaphragm. It is a spring-operated pump. This lever right here goes into the engine. Remember when you built the engine, that Lycoming, and you had two idler gears in the back, and one of them had a cam on it?
Yeah.
Oh.
That cam pushes on a rod. That rod pushes on this right here. And when it pushes it down, it's got a fork and it lifts the spring up. Cocks the spring. And then it's allowed to drop. The spring's going to do whatever the spring and the diaphragm want to do. I'll show you a video. And then that spring pushes down on, there's 1, 2, 3 diaphragms.
when you said fourth, what is that?
Fourth what?
Fork.
Fork.
Oh.
The thing you eat with? It's only got 2 little tines. Okay?
It's a juke. Never heard it called juke.
So remember that it's a spring-operated pump without a pressure relief valve. So it cannot control its pressure. The pressure is based on the spring. So if you have a pump that does not have a pressure regulator, if you have a very, very tiny orifice and the pressure of the pump is at 40, what happens if you open the orifice a little bit? Pressure is going to go down. And what happens to flow? Actually goes up because you open the orifice.
Screw this.
If you close off the orifice, the pressure goes up and the flow goes down.
That makes sense.
Wait, repeat that.
Oh, I thought you wanted me to move on.
Yeah, but I don't know, but you threw me off based on
Okay.
like, pressure based on spring.
This pump does not have a pressure regulator.
Yeah.
So there is nothing in here to keep the pump at the same pressure. The pressure is strictly dependent upon the size of the orifice and the spring pressure pushing down on the diaphragm. Okay, so if we have a very small orifice, that will be high pressure. I hate you too. Going back to the drawing board, chalkboard. All right, small orifice. Equals high pressure,
Low flow.
low flow. And if you have a big orifice,
Low pressure.
low pressure and higher flow. Why? Because there's nothing controlling the pressure. The only reason why you got pressure to begin with was because there was a blockage, an orifice, a restriction. That caused the pressure to go up. You open the orifice up, you're getting rid of the restriction. The pressure is going to go down, but because you opened up the outlet, more fuel is going to flow. Yeah.
Maybe I missed it. What controls the orifice inside this?
Nothing controls an orifice inside of this.
Oh,
Nothing controlled the orifice inside the other pump. The orifice is a theoretical thing. Well, it's actually the fuel control unit on the outside, but I'm just using it as a valve. So, oops. Not that one. Remember this drawing? Where'd it go? There. Where's the orifice?
External.
X, circle X. Here's my orifice. Internal or external?
External.
External. Now we're just going to take this pump and we're going to superimpose it on that drawing. Let's see. There we go. There we go. We do that. Over here. We'll just edit all this out. There we go. Okay, so that's a good question. Except that's not the outlet.
Well, gosh darn it.
Okay, outlet and inlet are here and on the opposite side. That has a very important function. You see inside of here, there's a diaphragm, this little thing, and a diaphragm, and then the pump mechanism, then a diaphragm. There's 3 diaphragms. This one in the middle right here is the main diaphragm. That's the one it pushes down, fuel goes out, pull it up, fuel comes in, push down. Well, if that diaphragm should have a tear in it, then without this upper one, all the fuel would then rush through here, go out the opening, and fill up the crankcase until it exploded. So what happens now is they put a diaphragm on top. It's a backup, safety diaphragm. So fuel, if it comes through this main diaphragm, it fills this chamber up and sprays out of here. Now it's very important that you vent it overboard. So that what happens is when the pilot is doing a pre-flight and they go, wow, I got fuel coming out of this thing right here. I should have that looked at next annual. What's happening is it's dumping all the extra fuel out overboard that gets through the tear. But it still works reasonably okay with this upper diaphragm. And the lower one, you'll see, it just takes out power pulses. So, all right, let me snap that up. Only about 5 minutes. All right. There we go. So there's, you can go ahead, lights. We'll watch the video, what's that, Thursday? So it's a spring operated, it pulls this diaphragm up. Fuel comes through one of these right here, comes through this one, in a bottom chamber, comes out the check valve, flows through here. When there's pressure, it goes out that check valve and out that way. So the nice thing about that is, I just scared you. And you'll see it in the video, how the fuel can actually bypass this pump all on its own because of where the check valves are. Just push right through it. So we'll watch, when I come back Thursday, oh, that's nice. So what happens is sometimes when this gets a tear in it and it starts to push fluid out, real smart people just put a plug in it to stop the fuel from coming out. And then it looks like that. So we're going to finish up with this thing on Thursday, which won't take much time. We'll watch that video, explain a little bit, and then we're going to start talking about the pressure carb. The PR58 right there.
I don't think I want to look at that.
It's so simple.
All right.
Very simple.
I believe you.
Is it?